Okay, so this is the second video now on light, the nature of light, I should say. As we're continuing on our garden notes right now, we haven't gotten through a whole lot right now, just to let you know. This was a lot of background information on this. So here, get ready to start taking some notes here. I probably should have said that last video, I'm sorry. So when can you see light? The object must be a source or producer of light itself would be one option for when you can see it, like the sun and all stars. Or the second option would be it's bouncing off of something and coming into your eyes. So it's not like everything produces light that you see. Like you look at anything, it's not like that thing's producing light. But some things do. Like your computer screen's producing light right now. That's how you're seeing this, whatever that computer is. Or basically the lights in your room are producing light most likely if you have lights on. But most commonly what we see is reflections of the light we produce, right? You only have to flick on one switch maybe for the whole room to be able to see it. It's not like everything turns on. It's just a light that is getting bounced off of. For example, the moon. A lot of people think, oh yeah, the moon produces its own light, but it just reflects the sun's light. So a couple things that we can see. One time that we can see light that's not produced by the sun in nature is what's called bioluminescence. Bioluminescence is really beautiful stuff. It's produced by living organisms. There's some photobacteria, photoplankton, that when you're stepping on sand, it'll actually light up all around, like in the movie Avatar. Pretty cool stuff. Or fireflies, also known as lightning bugs. There's even bioluminescent wood that you can see in really deep, dark forests. That's called foxfire, not firefox, but foxfire. It looks like the stuff is on fire. It's pretty darn cool. But that's not that common, right? Bioluminescent bacteria, probably pretty common compared to fireflies and all that jazz. But for the most part, we see light that's produced by very energetic things, fires or the sun. So light is sometimes emitted by devices. Say you have a chemical energy or thermal energy producing, or not producing, but being transformed into radiant energy, like we see in light bulbs. On the left here, you have an iridescent light bulb, which creates thermal energy from electrical energy, and that thermal energy then excites the coils and shoots out photons of energy, photons carrying the energy of light. In the middle is a light-emitting diode. It kind of does the same thing. It basically just does it without using nearly as much energy transforming into thermal energy. And then on the right you have compact fluorescent light. So these are all examples of using electrical energy to get radiant energy or light energy, right? But in the process, you're using different amounts of, or they're transforming into different amounts of thermal energy, making them more or less efficient. Light is carried by electromagnetic waves, and like we said, those waves can be represented in a transverse way with wavelengths that you can measure and that correspond to their frequency. All light travels at the same exact speed, so if it has a shorter wavelength and is traveling at the same speed, that's like it has to go back that and forth that many more times if it's trying to catch up with the person next to it. So gamma radiation is electromagnetic radiation. It's the same thing. It's a light wave that goes out in one direction, which is why we call it a ray. That is the most energetic form of light. X-rays are less energetic. UV light, ultraviolet light, is less energetic than that. And then you come to visible light in the spectrum. Below that is infrared and microwave and radio. So just because infrared is less energetic as a wave than visible light doesn't mean that you can't have more of it, right? Say you had a lot of infrared radiation, would you feel that more than you feel the visible light somehow? And the answer is yes. When you feel the warmth of the sun, you're feeling the infrared radiation. Most of the light of the sun comes off in the green spectrum, in the green color of wavelength, but it's no surprise that a lot of life on Earth is adapted to that, right? But infrared light is also felt by the sun, and UV light damages your skin from the sun. I've said this a couple times. And down here on the bottom, it shows the scale of electrons voltage, which is one way of measuring the potential energy of very, very tiny things like these photons. So another way of looking at this is by just looking at each of the waves. If you were looking at dark red, you're looking at something like 665 or above nanometers. It gets longer, the wavelength is longer, so the frequency is actually less. It means that from this side to this side, right? If I'm traveling right here from my mouse to this side to that side, if I had to go up and down more often, that means there's more cycles per second, which leads to a higher frequency. So low wavelength leads to high frequency, which usually means more energy. And in the case of frequency for light, it changes its color from red down to violet, or above violet, meaning we can't see it anymore, or below red, meaning we can't see it anymore also. They don't need to travel through something because of that unique nature of they're getting carried by the electric and magnetic fields that are kind of vibrating back and forth. So it doesn't actually need something to go on, like a duck that sits on water, goes up and down with a wave of water. This energy goes back and forth in those packets, those quantum packets that we call photons, because of those electromagnetic fields and nothing else. So they don't need something to travel through. In other words, they don't need a medium. They can travel through empty space is one proof of that, right? If we needed to, like with sound, where you had air between the sun and earth, right? Then we could maybe understand why the light was able to travel that way. But there's nothing there, right? It can't go across anything, and we would still be able to see the sun, so it's able to go through nothing at all. Easy proof is just looking at the sun right now. The speed of light is the fastest thing known to scientists. It is very fast. This is a TurboGrafx, but the importance is it can circle the Earth 7 times in less than 1 second. That's how fast it is. 300,000 kilometers, not per hour, per second, right? So that's like, I'm not even going to do math for you right now, but that's a lot. 186,000 miles per second. It's unfathomably fast compared to sound or anything. So you can stop and jot and do this real quick if you want to do the math. If Earth is about 150 million miles away, or kilometers away, or 93 million miles, and we just said that this is the speed of it, how fast would it be for light to reach us from the sun? So go ahead and try and solve that right now. I'm not going to use a timer. Okay, if you're coming back here, it takes about 8.3 minutes for light to travel from the sun to Earth. So that's why we say when we're looking out there into the universe, we're actually looking back in time, because basically it takes time for light to travel to us. So what you're seeing from the sun, if you're looking up in the sky, right, the light that you see in the sky is 8.5 minutes ago, back where the sun produced it. So you're basically experiencing that information from backwards in time. It's like it's sending a message, and it takes 8.5 minutes to send to you, but that message is everything that we experience. Kind of freaky. So really, you know, we just got to the 8.5 minute mark, right? So if the sun went out right now, it would take the whole length of this video before you even knew it. We would also all probably die. All right, I'm going to skip over this one because we're already starting to run short on time here. So we said that light travels faster in the vacuum of space than it does in matter, which is the exact opposite of sound. Sound travels faster in something that's more dense, like a diamond, than it does in a vacuum, which it can't travel through. So even though sound likes to travel through stuff that's more dense because it's just able to pass along a signal faster, that's really just like cumbersome for light. Light doesn't need to travel through something, so why would it want to, right? If it goes through water, it slows down. If it goes through something more dense than water, it slows down even more. So, you know, 186 to 120, that's basically a 33% reduction in speed just going through glass, right? And you think, can you slow down light? And the answer is yes, it can slow down depending on what it's going through. It just basically, it's like you trying to run through a big swamp, right? You're not going to be able to run this fast through that. You prefer running through just air, right? There's less resistance to it. It travels in a straight line. Even though it goes up and down, we say it has those electromagnetic fields that we can think of it in terms of its frequency then. And it's a simplification even then. We still will say that light travels in a straight line, and it travels in one direction only, which makes it a ray. So a light ray is a straight line of light that travels outwards from its source and travels in that straight direction. It won't curve though without being interacted with something. It will just continue on that direction until something causes it to change direction or bend. We took a look at this as a slinky before. So imagine that the hand in this diagram here is an electromagnetic field vibrating those packets of energy we call photons. So the wave would travel in that direction at that very, very fast speed. It's not traveling up and down this way at, you know, a couple 100,000 kilometers per second. It's traveling this way at a couple 100,000 kilometers per second. That doesn't make a difference if it's red light or blue light. It's always going to travel the same speed. X-rays or gamma rays, always the same speed. Radio waves, this way, the same speed. That's why, you know, if you were trying to listen to radio that was sound, you know, if you were moving one way, it would make it sound like it was a lower note, right? It would change the frequency of it. Radio is so fast, radio waves are light, that it doesn't matter how fast you're going. It's never going to create a Doppler effect in the radio in your car or anything like that. So this is the end of this lesson.